we were discussing the spin angular momentum. Spin angular momentum. And this is represented by S. In the last lecture, we discussed that spin is an intrinsic property, right? And it is like a classical spin, but is we cannot observe this thing, that how the particle is spinning. We say that it is with us from mathematics only. We cannot visualize this thing, that how it's spinning. Because there were an experiment that I discussed in the last lecture, the experiment performed by Stern-Gerlach. So this experiment actually confirmed that when you move a beam of silver atoms, and such atoms in which the orbital angular momentum is zero, L is zero, because for orbital quantum number L we consider the s orbit. In transition metal we are having the electron in s orbit. So when we will pass this one, here there will be no contribution from the orbital angular momentum, even though the beam split it into two. And that was the confirmation that in addition to this orbital angular momentum, there is another angular momentum which we call the spin angular momentum. We were having some spin statistic theorem, spin statistics theorem, and from there you know the result that the total spin came out to be 0, half, 1, 1 and 1 half. So this is half, 1 and 1 half will be 3 by 2, then 2, then 5 by 2, and so on. So the spin was like this. With the help of mathematics or the solution of the Schrödinger equation, we came to know that the angular momentum can be this, this, or this. It was only the integral numbers, and that was depending on theta and phi, the spherical harmonics that we did. While the spin was not depending on them, and it is an intrinsic property. So how this half came in there, we came to know about this from our mathematics. The other thing is that when you know about the Pauli work, the Pauli exclusion principle, you remember. What is the Pauli exclusion principle? Pauli exclusion principle says that it is not possible for a particle, for an electron, to have the same set of quantum numbers. So when we consider the first orbit, and inside the first orbit we are having 2 electrons. So those 2 electrons are then in 2 different orbitals. But we know that when they are in the s orbit, then s orbit is an orbital. And in s orbit we are having the 2 electrons. So they will have the same set of quantum numbers then up to orbital angular momentum. But we say that one electron will be with plus half spin and the other electron will be with minus half spin. These we call the M or MS. These are the spin quantum numbers. S is spin, while MS is the spin quantum number. As we were having L is the angular momentum, while small l is the quantum number. We call this as ML as well. So, MS here plus half minus half. So now the two electrons are having different set of quantum numbers and they can exist. This was the Pauli exclusion principle. Spin-angular momentum, one from the experiment, the other confirmation from the statistics, and then from the work, the theoretical work. It was the theoretical work by the Pauli, we know this thing by Pauli exclusion principle, and with this he actually did this thing, this mathematical courage in 1927. And then in 1928 it was Paul Dirac. You know about in formalism of quantum mechanics we have studied Dirac formulation, Dirac notation, the bracket notation. So Paul Dirac was the person who did mathematics of the relativistic quantum mechanics, and it came out from his work that spin should be an essential part in this. Without the spin, the relativistic quantum mechanics wasn't possible. So he included it as an essential part of his work, and hence it was confirmed that elementary particles are having an intrinsic spin. So up to now, as it is confirmed that the elementary particles are having an intrinsic spin angular momentum, it has nothing to do with the coordinates. It has nothing to do with the dependence of the wave function on theta and phi. It is spinning on its own axis like a classical spin. So we will have to write then the eigenfunctions like spin. Spin itself will be having some value as it is angular momentum. It will have some value. That value will be an eigenvalue. But what function will represent this? The eigenfunction. What kind of eigenfunctions will we know for the spin? Because so far we know the eigenfunctions that are depending on theta and phi. So how we will write the eigenfunctions of this, and when it comes to photon, then it is represented by common vectors. You know vectors having magnitude and direction. But when it comes to the electrons or other elementary particles, then we represent them by spinors. Spinors and bispinors. Now, in a while we will come to know about what are spinors and what are bispinors. Spinors are also behaving like vector, but at the moment we are not discussing the symmetry operations or the symmetry in quantum mechanics, that whether they are invariant under rotation. That is above your level. But to understand this one, that what are vectors and spinors, they behave the same, while their directions under symmetry operations are different. So this is the only difference between them. When we say that out of these spins, if you take the integral numbers only, positive, it cannot be negative. So 0, 1, 2, 3. all such spins we call that the particle which will have such spins, we will call them as bosons. And the particles which will have half integral spin, like 1 by 2, 3 by 2, 5 by 2 out of this, that we call them as fermions. Electrons and protons, they are fermions. Quarks are fermions. Okay. So bosons and fermions. When we say about the elementary particles, so far we know only about the spin-half fermions. And spin-half fermions are electrons and protons. We don't know that such particles exist. They may exist, but we don't know about such particles. Those particles will have higher values of spin-half. We are only knowing such fermions which are having spin-half values, while the other particles we don't know at the moment. So we will restrict ourselves only to the spin-half particles. It is also possible that a particle which will represent itself as a zero spin particle, is a zero spin particle, like a particle which will show itself as a boson, but its ingredients are, you can say, the constituent particles may be fermions. So they will add up and they will give you spin like this. I can give you an example of the helium atom. Helium atom, if it is in a ground state, then its spin is 0. Now what is helium? Helium is composed of a nucleus and electrons. You know about this. Now nucleus is proton and neutron. Proton and neutrons are actually made of quarks. So quarks are fermions. Electrons are fermions, but their combined effect gives you a boson. So this is also possible, that you will have a boson spin, but the individual spins will be of fermions. So with this, we will start now, or we will start developing our mathematics with from the spin of only this particle, which we call the fermion, and out of all fermions we will restrict ourselves to the spin-half particles. You will have to keep few things in mind, that we are having the angular momentum, as I have written earlier, like the L, it was L into L plus 1 into h bar. It was L square is L into L plus 1 h bar square. So L is this one. You know that this number is a dimensionless number. It's just a number. Because it can be 0, 1, 2, 3, 4, so on. So it's a number. The dimensions of angular momentum are here. So h and then h bar. This you call the Planck constant, and this you call the reduced Planck constant. What is the difference between the two? I have discussed this difference in the conceptual physics series. You can go through that video in which I have explained that what's the difference between H and H bar. So the angular momentum, here it is the angular momentum. Reduced means it is divided by 2 pi. When you divide H by 2 pi and why a different name is given to this, you can watch the video to understand this one. So when I consider that S is half, spin half, then there will be 2 values of the M or MS. So it is always difficult to write the S over here. So we will go only with M. So M will have then 2 values, plus half and minus half, as we observed in the Stern-Gerlach experiment. So I can write that there will be 2 eigenstates as the eigenfunctions. Means eigenfunction is a function associated with a given state. So we will have 2 eigenstates and I will write them as S and M. S is the spin and this is the orientation of this spin, whether it is plus half or minus half. So I will write it like this, that this is half, S is half, M can be plus half and M can be minus half. So these are the 2 eigenstates. S in both is half, while the orientation is plus half and minus half. So we will call this one is spin up. We will call this one is spin up eigenstate, while this one we will call is spin down. Spin up and spin down. The 2 spots in Stern-Gerlach experiment that we observed. One was the spot on the top and one on the bottom, while the beam was hitting this center. But there was orientation under a non-uniform magnetic field. This was the alignment of the beam, which was having no angular momentum, the orbital angular momentum, yet it went to 2 different locations and it was due to the spin of that electron. So, we will have to, these will be our eigenstates, and now I will go to the spin state of this system. So let's say the spin state of this system I write is chi. This is chi, chi. Chi, and this is equal to A, B, and further I can split this one, A chi plus B chi minus. While chi plus is representing the spin up state, which is this one, half plus half. But as it is a state, the half value will come here is the eigenvalue, and B is the eigenvalue. So when you take out half from this one, so we will say that this is the spin up state, chi plus, and it is 1, 0, while this one is chi minus and it will be 0, 1. Because you are multiplying A with this, the result should be AB like this. When A is multiplied with 1, 0, you will have A here. When B is multiplied with 0, 1, you will have B here. So this I wrote is the spin state. Now all our on our spin operators, on 2 cross 2 matrices. Why 2 cross 2? Because one will be passed spin up while the other will be called spin down. So now our job is to find out